have Professor Michael Wakin from School of Mines from the Electrical Engineering Department. Professor Wakin received his BA degree in mathematics and his BS, MS, and PhD degree in electrical engineering from Rice University. He spent some time as a postdoc at Caltech and as an assistant professor at the University of Michigan in Ann Arbor. He then became an assistant professor at the Division of Engineering in the Colorado School of Mines, where he's now, right? He got in 2007 the Herschel and Rich Invention Award from Rice University for the design of a single pixel camera based on compressive sensing. And in 2008, the DARPA Young Faculty Award for his research in compressive multi-signal processing for environments such as sensor camera networks. So today he will be talking about the multi-scale structure of non-differential image manifold. So thanks for coming.
Okay, thank you very much. It's always a pleasure to visit your university, and I've enjoyed the chance to meet and learn about COSY program today as well. In the past few years, I've given a couple of talks here on compressive sensing, and while compressive sensing is very much a part of my research, I want to talk about something a little different today, focusing more on image processing. It still has a lot of connections, and the thinking we developed in developing the research that I'll talk about today still very much shapes my thinking in compressive sensing research. And towards the end of my talk, I will make some connections with compressive sensing and show you how these manifold ideas really fit into that area. Just to define that term, compressive sensing, this is a field, a relatively new field, in which we think about acquiring high-dimensional signals and images using very small numbers of random measurements. And once we've done so, we need to use models for how those signals or images behave in order to recover those high-dimensional signals or images from those random measurements. So again, today's talk will be about manifolds, especially the manifolds where images live. And then at the end of the talk, I'll talk about how those models can have a role in compressive sensing. So I am a signal processor, and as a signal processor, we think a lot about models for signal and image structure. And models help us formalize this notion we have that really not all in-pixel images, say, are created equal. So if we go into MATLAB and randomly generate an image with n pixels, we'll see something like this. And we can do that over and over again, and we'll always see something like the image on the left. But we know that real-world signals and images look more like the image shown on the right. They contain structure that obeys certain rules. And so as signal processors, we develop models that characterize that structure. Frequently, those models contain some notion of conciseness. That relative to the number of pixels in, which can be huge, there are somehow relatively few degrees of freedom in these images. And once we've developed models that capture that, then those allow us to do things like remove noise from images, compress images while retaining the important information, solve some of the problems that I'll be talking about today as well. But I'm not only interested in models, I like to think about the geometric implications behind models. And so part of today's talk will be kind of advocating for taking a geometric perspective on signal modeling. Here's what I mean by geometry. If we're dealing with images that contain n pixels, we can think of every image as just being some point or some vector in Rn. So cameraman lives here, boats lives here, Peppers lives here. Every image with n pixels lives somewhere in this space, and a lot of images in this space look something like this or this or this. They look like noise. But by geometry, I mean thinking about the implications of models in the terms of if we're dealing with a model for signal structure, where does that suggest that these images live within this high-dimensional space? And what's frequently the case is that if we have a concise model for signal structure, that will translate into a low-dimensional geometry or low-dimensional geometric structure along which our signals or images of interest tend to lie. So let's look at a couple of examples of low-dimensional structure and how it can arise. One would be a linear subspace model. So in this case, suppose we have, for example, a 2D Fourier basis for our space of images, and we consider a class of smooth or band-limited images, then we know that those images live along the span of just the low-frequency elements in this Fourier basis. So those low-frequency elements span a low-dimensional plane, and our images live somewhere along that low-dimensional plane. That linear geometry has special implications in the processing of those signals. It makes doing things like noise removal very, very simple. However, we also know that linear geometry is not really very realistic for lots of classes, and that most signals don't live along, along these linear structures. So for example, if we have two images like this, and we just linearly interpolate between them, or take the average of these two signals, we don't get something that also looks like a natural image. We get something that does not look like a natural image. So we know that really there's no line connecting these two images in that space along which everything in between is a realistic natural image. This is well known, and so there's a variety of nonlinear models that have been proposed for modeling and processing image families. One way of capturing that nonlinearity is through something like a wavelet basis instead of a Fourier basis. And if we're dealing with images that are piecewise smooth instead of actually smooth, then in the wavelet domain we tend to have things persist not along one fixed low-dimensional plane, but along one of many possible planes, each aligned with different sets of the wavelet basis elements. And that's because in a wavelet representation, which we often refer to as a sparse representation, we don't know in advance which of the wavelet elements are going to be the significant ones. And so really in the wavelet type model, we have not just one plane, but a whole set of possible planes on which our signal might live. Sparse models are very powerful, and they are very popularly used in compressive sensing. But I'd like to talk about somewhat narrower classes of images today, where the geometric implications are a little more, they require a little more close examination and don't exactly fit into this union of subspace models. In particular, I'm interested in classes of signals related by some parameterization. So suppose we're going to take pictures, suppose we're going to consider images that are described by some parameter theta. So we have some k-dimensional parameter that controls the degrees of freedom in our signal. And for any value of theta, we let f theta denote the signal that would be generated according to that value of theta. So for example, theta might describe the position within the plane of this screen where I could position my camera. For any value of theta, my camera would see some image. That image corresponds to some point, f theta, up in our n-dimensional space. If I change theta, I change the image that this camera would see, and that changes the point up in this space. If I trace out some path in parameter space, then I trace out some path in this space. And if I consider all possible values of theta, say in this 2D plane, then all of those images will trace out a two-dimensional surface in this n-dimensional space. And that surface is called a manifold. So manifolds can arise when we have degrees of freedom in positioning our camera, degrees of freedom in positioning objects within the image, local degrees of freedom such as the orientation of an edge in an image, and so on. Manifolds can also arise when we have non-parametric image families, things like databases of images of human faces and so on. But I'm going to stick to the parametric case today because that will give us a chance to say some things formally and mathematically. What is known about the geometry of these manifolds? Well, first, it's maybe no big surprise that these things are generally nonlinear. You know, again, if we just interpolate between two images, we don't expect to see another one that looks like it belongs to this parametric image family. A little bit more surprising, at least to us, was the fact that these image manifolds are often non-differentiable. I'll talk about what assumptions on the images make these manifolds non-differentiable, but that lack of smoothness, that lack of differentiability, which means that even if we zoom way in on the manifold, we don't really see a smooth, sort of plane-like structure, has significant implications in our ability to solve image processing problems that involve these types of parameterizations. Right? They have implications in our ability to solve image processing problems that deal with families of related images, families of images that are related by some underlying parameterization. So I'll start off by talking about an application, specifically that of estimating the parameter theta when given one of these images. And with this application, we'll see why we care so much about this problem of lack of differentiability. I'll explain why that is actually a problem. Next, I'll talk about where this lack of differentiability comes from. It comes from the fact that we have edges in these images, and these edges move as a function of theta. I'll discuss why that's a problem, but also how we can get around that problem, and then come back to the parameter estimation problem, and despite the lack of differentiability, effectively solve that parameter estimation problem. Next, I'll talk about a second type of non-differentiability that can arise in these manifolds at certain places, also due to edges, but for a slightly different reason. And finally, I'll kind of wrap up by visiting the topic of compressive sensing and explaining how manifolds can play a role in the compressive sensing recovery problem. Okay, so to show one reason we might care about this lack of differentiability, let's look at the parameter estimation problem. So suppose we're given an image I, which corresponds to f theta for some value of theta that we don't know. And I'll frequently resort to this model, just to this example image class to illustrate things. Here we have a white disk on a dark background, and we don't know the position of where that disk is located, and we'd like to estimate it. Can we recover the underlying parameters theta efficiently and with high precision? And if so, can we also do this when the images are noisy? Suppose I've got a noisy image and I want to estimate the best value of theta to describe that image. You know, this is just a prototypical problem that could arise in image registration, computer vision, edge detection, other types of problems in image processing. A reasonable way to attack that problem might be to try to solve an optimization problem where we say, given I, let me find the value of theta prime so that the corresponding image f theta prime is as close as possible, maybe in mean square error, as close as possible to the image I that I started with. Now if, and this is a big if the manifold was actually differentiable, then we could reasonably attack this problem using calculus. We could expand this objective function that we want to minimize. We can use one of any variety of iterative minimization techniques to try to find the minimizing point on this of this penalty function. What many of these techniques would have in common, Newton-like methods, would ask us to solve a set of iterative update equations. What's significant about these equations are two things. One is let me just say what this notation means. These braces here on the side mean that we're taking an inner product of two images. Here's one image, here's another. The inner product is just taking two images, lying them one on top of the other, multiplying all of the pixels pairwise, and then adding up all of those products. In other words, it's just correlating two images, measuring the correlation between two images. But the other significant thing here is that what we're correlating with are tangents to the manifold, which only exist if that manifold is differentiable. I think rather than go through the equations, what makes at least good intuitive sense is to look at this pictorially. So let me illustrate what Newton's method would ask us to do if the manifold were actually differentiable. So suppose we've got our image I that lives somewhere on the manifold, and that corresponds to some value of theta that we don't know. But maybe we have some initial guess, theta naught, which corresponds to some other point, f theta naught, on the manifold. Newton's method would ask us to perturb our parameter around our guess in each of its two dimensions in this case, and then look on the manifold which directions do we move. Basically, this is how you can compute tangents to the manifold. These tangents themselves are vectors up in Rn, our n-dimensional image space. Therefore, they are themselves images and things we can use to compute inner products. They span some tangent space, and Newton's method just asks us to project I onto this tangent space, and then wherever we land, in that tangent space, relative to these tangents, just tells us how to update our estimate for the parameter theta naught. Then we have a new estimate, theta 1, that corresponds to some other point on the manifold. We can find the tangent space centered at that point and project again, and hopefully we will converge very quickly to the true parameter. The problem is that we can't do Newton's method because these tangents do not exist. So let me first explain what I mean when I say these tangents do not exist, and then we'll talk about a way to deal with the apparent difficulties presented by this fact. Okay. As I've already hinted at, the problem of non-differentiability comes from the fact that many images of interest to us, such as this disk image here, contain sharp edges, and these edges move as a function of theta. Here, theta describes the position of that disk, so clearly the edges will move as a function of theta. When you have these two ingredients, you will have a manifold that is non-differentiable. In fact, it will be non-differentiable everywhere, at every value of theta. And there are a couple of ways of seeing this. One is analytically. You can work through computations like this that say, suppose I have some point f theta on the manifold, and I perturb theta by an amount h. Let me just look at the distance that I move in our image space, measured in L2. That's going to be proportional to the square root of the size of our perturbation. And because that exponent is 1/2 instead of 1, that will give us a non-differentiability. And you could see that, maybe a better analytical way to see that would be to think about, what if I used local differences to try to estimate the tangent? Similarly in 1D calculus, the way you can just sample a function at 2 points and then subtract those values and divide by h. And as h goes to 0, this ratio should converge to the slope of that function at that point. Well, here, if we do this, we take f theta plus h minus f theta and divide by the amount of that perturbation, h. That should, as h goes to 0, converge to a fixed tangent vector with finite norm. But in fact, it does not. It will explode for any one of these image classes that I've talked about. So tangents do not exist. There's going to be another way, an experimental way that we can also illustrate where this lack of differentiability comes from. But perhaps before moving on to that experiment, let me make a remark about the sort of analysis that we're presenting here. This analysis pertains specifically to images that have not been pixelized. So we imagine like a continuous domain image space where this disk could be translated anywhere in the plane, but as we zoom in, we always see a curved edge and we never get to like a pixelized resolution. In this continuous domain model for images, these sorts of equations are valid. If there's pixelization, then all of the morals of this, the lessons that I'll be trying to present, will still basically follow for these pixelized images up until that scale of pixelization. Once you get to the scale of pixelization, things may sort of clean up a little bit. But as I'll talk about, we may want to take a multi-scale approach to some of these problems. And so really, at these coarser scales, these differentiability issues are still significant. So all that to say, the pixelization issues should not be, I hope will not cause a major distraction in getting the main lessons from this talk. Okay, so let's move on from the analysis to an experimental way of seeing how these tangents fail to exist. Sticking with this translating disk model, suppose we do the following experiment. We fix some value of theta that corresponds to an image, f theta, up on this manifold. We construct a ball of radius epsilon in the parameter space for some value of epsilon. And then we just sample randomly, sample a bunch of points randomly from this ball. Those will correspond to a bunch of images up on the manifold in the neighborhood of f theta. Now, this manifold, in this case of a translating disk, is two-dimensional. So what we could try to do is take this sampling of points that we've just constructed and try to fit a 2D plane to that sampling of points. And the computational technique for doing this is just known as PCA, or Principal Components Analysis. So we do that at some value of epsilon, and here are the basis functions we learn that span that give us the best 2D approximation to that local sampling of points from the manifold. And both of these look like an annulus in this case, one dealing with sort of vertical changes in direction, one dealing with horizontal changes in direction. Now, here's what's kind of important about this experiment. Suppose we change epsilon. So we shrink epsilon, this ball gets smaller, and then we repeat the experiment. We sample from this ball, we get a sampling of points from a smaller neighborhood on the manifold, and then we again try to fit a plane to that sampling of points. Well, what PCA discovers in this case is again a pair of annuli, but now they are qualitatively different, right? They are thinner than they were before. And if we were to continue this experiment indefinitely, and if there were no pixelization issues to contend with, then hopefully you believe that these rings would just continue to get thinner and thinner as epsilon shrinks. So what we've identified is really a family of approximate tangent planes. We sort of generalize the notion of a tangent structure on a manifold to a multi-scale tangent structure, where we index the tangent space of the manifold both by theta, the location, which is typical, but also by epsilon, or the scale, which is atypical. If the manifold were in fact differentiable, then as the scale goes to 0, as that ball shrinks and shrinks, these approximate tangent planes should converge to the true tangent plane that would exist if the manifold were differentiable. But this does not happen when sharp edges exist that move as a function of theta. In fact, we can compute for this experiment that I showed, we can empirically compute that as epsilon shrinks by about a factor of 2, we get about a 30-degree twisting of those tangent planes. Every time epsilon shrinks by 2, that tangent plane will twist by another 30 degrees. And that will continue on indefinitely, never converging to a fixed tangent space. In fact, not only these tangent spaces not converge, but assuming we're in the infinite dimensional space of continuous domain images, these planes are in fact twisting into new dimensions. So what started as a relatively simple notion of a manifold, which maybe you think of as a nice 2D sheet blowing in the wind or something, is actually on closer inspection very, very complicated. We can zoom in, and it never really simplifies. The tangent structure never gets simple at all. However, this idea of a multi-scale tangent structure is something we can put to work for us, and I'll talk about how we can exploit that in a second. But let me say there's a way that we can do this in a more computationally friendly way that's a little bit more friendly than principal components analysis. So I'll talk about that in a second, this other way of accessing this multi-scale tangent structure without PCA. Just a quick remark though. What we're doing here is dealing with complicated, non-differentiable objects, these manifolds. But we've come up with a way of analyzing these in a multi-scale structure, really looking at sort of difference behavior or tangent behavior on the manifolds at a variety of scales and locations. So morally, though not extremely formally, this is kind of analogous to what wavelets are useful for when we are analyzing functions, including non-differentiable functions. So I'll come back to this wavelet analogy in a second. Here's a little bit more friendly way of accessing this multi-scale tangent structure without resorting to PCA. So I mentioned that the problem of non-differentiability comes from the fact that we have sharp edges in the image, and those edges move as a function of theta. So it should come as no surprise then that if we were to blur the image and therefore smoothing out the edges, then the manifold of smoothed images will in fact be differentiable. So if we took my camera, put it out of focus or something, or blurred the lens, and then consider all the images that camera might see, that manifold of images would in fact be differentiable. It would have well-defined tangents, and the more we smooth the images, the more the manifold will smooth out. So we could think about defining the multiscale tangent structure in the following way. Let's think about a convolution or a blurring operator, which is just a Gaussian filter, say, of width s, and we call that filter phi s. For any image on the manifold, we define f theta s to be the blurred version of the original sharp image. And then we define big Fs to be the manifold of all such blurred images over all values of theta. That manifold is differentiable, and we can use it to define an approximate tangent plane to the original manifold. So we'll consider this multiscale tangent structure of our original manifold, where tangents are indexed both by theta, which is location, and s, which is scale. And that approximate tangent plane is just defined to be the actual tangent of the differentiable manifold that we get by blurring out all the images. So again, I will illustrate all of this pictorially, but I want to at least give the notation for what I'm talking about here. This is different from the PCA construction of a multiscale tangent family, but it's actually more similar than one might think. There are good reasons that these two things are connected, what we were doing in PCA versus what we're doing here by blurring out the images. Basically, because blurring an image sort of mixes pixel values spatially, whereas in PCA we were just moving the things around, that was also giving us some spatial mixing of pixel values. And that's, informally the reason these two things are connected. Going back to this analogy with wavelets, there's another interesting consequence that we can show semi-analytically and semi-experimentally. Really, this approximate tangent structure, this multiscale structure on the manifold that we've identified, is indexed by two continuous parameters, theta and s. Much like the continuous wavelet transform is also indexed by scale and location, which are both continuous parameters. But we might be interested in discretizing this or sampling this multiscale tangent space, both in scale and in space, so that we could enable computational techniques that just store this characterization, this discrete characterization of the tangent structure of a manifold. We might want to ensure, for example, that there's a fixed amount of twisting between samples. So that, from moving from this tangent plane to this one, we move no more than 5 degrees, or from here to here, we twist no more than 5 degrees, and so on. So analytically, at least for this disk image, we've shown that the appropriate sampling you'd need would be equally spaced in the log of the scale, s. And then empirically, we've seen that at any fixed scale, you should take a sampling that's proportional to the scale you're at. So at finer scales, you need to sample more densely in space. This is exactly the picture we would get if we talked about discretizing the continuous wavelet transform to get a discrete wavelet transform. It uses a dyadic discretization of scale and then a proportional discretization in the spatial domain. Now the reasons are somewhat different, and in fact the actual sampling we'd need on any particular manifold depends on that manifold. So we can say things here that are less general purpose than for wavelets, but I thought it was an interesting analogy that would be worth mentioning here. Let us now return to this problem of parameter estimation and see how we could use this multiscale tangent structure to solve that problem. Okay, remember the problem with Newton's method. If we had a differentiable manifold, we would be asked to project I onto the tangent plane that was centered at our guess f theta naught. But these tangents did not exist. So what we could think about doing would be a multiscale Newton algorithm where we construct a sequence of manifolds, fs at a variety of scales s, from coarse to fine, that is more blurring down to less blurring, that converge to our non-differentiable manifold f. And then we just take one Newton step at each one of these scales. So let us see pictorially what this would look like. So here's our observation I that corresponds to some value of theta which we don't know. We have a guess theta naught which corresponds to some point f theta naught on this manifold, but this manifold is not differentiable. So what we could think about doing would be to blur out this image and blur out this guess. So we just convolve each of them with a Gaussian filter of some fairly wide width. So we're pretty aggressively blurring out all the features in these images. But these two things live on a manifold of blurred images that is differentiable. So tangents are well defined on this manifold, and they are easy to compute numerically. They look something like this, and you can see that indeed these do look a lot like the tangents we were getting from PCA. So that the two approaches empirically look very similar here. So now we can project this blurred image onto that plane, and wherever we land in that space tells us how to refine our estimate, theta 1, to get theta 1. Now back to square one. We have an estimate theta 1 which corresponds to some point f theta 1 in this space. But this manifold, our original manifold, is not differentiable. So we can do the same thing again where we blur things out and then project and update our guess. But here, because we are closer to the truth now, because theta 1 is a better estimate than theta naught was, we can tolerate more twisting in the manifold that we're going to access in order to refine this estimate. So we're going to blur out both of these images once again, but we're going to use a blurring filter that's not quite as aggressive. It doesn't blur things out quite so much. So we do this blurring, which smooths out the manifold, though not as smooth as that other smooth manifold we just had. We've got tangents that are well defined on this manifold. They will look different than before. In particular, they're going to be asking more local questions about the image in order to really more precisely refine the estimate around the truth, to really try to converge towards the truth. We project this image onto that plane, and wherever we land tells us how to update our parameter estimate. And then we can repeat this process, hopefully just a few times. And I'll show some experiments that indicate why we can be optimistic about and aggressive about setting these scale parameters. Quickly, before showing these experiments, let me just say that methodically what we're doing here is not that new. So in terms of, there's a vast literature on things like image registration or similar parameter estimation problems to what I've talked about here. And even in classical techniques for these problems, it's very common to see coarse-to-fine algorithms with a variety of subtly different approaches. What we've shown here is not that we've got a technique that has to be better than any of these other techniques, but instead we've arrived at this technique by taking this geometric perspective on the problem. I think what distinguishes our technique from the others is that we arrived at this by studying the geometry of the manifold, by thinking about this in terms of a multi-scale tangent structure to these spaces. And in a way, this is a bit of a work in progress. So in principle, some of the benefits of this should be that we can also extend our analysis and have very rigorous bounds on the convergence analysis of the algorithm that we're proposing in terms of the geometry of the manifold. We can get insight into what sequence of scales would be acceptable to choose as part of our algorithm, or how accurate our initial guess needs to be, and so on. Okay, let me show a few experiments to illustrate this algorithm. So here we are in our translated disk model. Here is I. This is the observed image. It's got a disk right here plus noise. We're going to feed the algorithm this initial guess. On the bottom left, you see the difference between these two top images. And on the right, now this is not available to the algorithm, but I'm showing just so you can see very clearly what the actual error is in our guess compared to the true position of the disk. Okay, so let us take one step of this multi-scale algorithm. We're going to blur out both of these images, compute tangents, project onto those tangents, update our estimate. And here we are after one step. The parameter s equals 1/2 indicates that we had a Gaussian bump with approximate support of about half the image. So it was a pretty aggressive smoothing out of all these image features. But with one step we have updated, we're certainly more accurate than we were before. Now it turns out for this problem we can be pretty aggressive in choosing our scales. We can actually square our scale each time. So after the next iteration we're at scale 1/4. We've again become more accurate in our parameter estimate. We can go to scale 1/16 and take one step, and then finally we take one step at scale 1/256. So a total of 4 steps, 4 projection steps for this algorithm, and we've converged to this level of accuracy. To sort of gauge the quality of this accuracy, here's a plot of the mean square error versus iteration. This is the MSE of the noisy image versus our guess for the parameter. By the 4th iteration, we reach this green line, which indicates the noise level in the true image. So basically, there's no real meaningful estimate of the parameter that's better than the noise level that we introduced into the signal. So in just 4 iterations, we've gotten a parameter estimate that's as good as we should hope to get. If there were no noise, we can do all of this very well also. And usually within 4 or 5 or 6 iterations, the convergence is well within sub-pixel accuracy for the position of the disk. You know, pretty much you can get down, I'm not sure I would say machine precision, but to 5 or 6 or 7 digits of accuracy in the position of the disk within 4 or 5 or 6 iterations. Here's another experiment. So now we're not just shifting things around in the plane, but instead we have objects that can actually rotate around. So this is a 3-dimensional manifold where the cube can be rotated among any of its 3 axes. Here's the initial error in our guess. Here we are after one step in this procedure. The second step really brings us in very accurately. The 3rd step and the 4th step really clean things up, and by this point we've got much better than again, sub-pixel accuracy and basically an estimate that's within the noise level here. Just want to show one more example here. This is an estimate of a 5-dimensional parameter. Our image model here says we're going to see an ellipse, but we don't know the parameters that govern that ellipse. And there are 5 such parameters: the major and minor axes of the ellipse, the horizontal translation, the vertical translation, and the rotation of the ellipse. So again, we need about 4 scales to get down to sub-pixel accuracy of our parameter estimates. What I'm showing here at one particular scale, this red image is the thing that's going to be correlated against each of these 5 blue tangent images. And I show this because there's some, intuitive meaning behind these tangent images. You can see that really what these are sort of asking about our parameter estimate is, should I move my parameter, should I, refine my estimate up or down, or should I refine it left or right? Should I rotate my estimate of the ellipse? Should I make it longer, or should I change the minor axis? So these tangents are asking very meaningful questions about the parameter estimation process. And also what we see is that as we move down through the 4 scales, the nature of these tangents is changing so that they're asking very much more localized questions as we get to these finer scales. Okay. There's actually a second type of non-differentiability that can arise, also due to the motion of edges in images. Now, I'm going to be much less analytical here. I just want to show a few pictures to give the intuition of why this kind of non-differentiability arises. The first type of non-differentiability was because we had sharp edges that move as a function of theta. This type of non-differentiability can arise when we have edges that suddenly appear or disappear at very special values of theta. So in fact, it's not a global non-differentiability like we had before. It's very much local. And what it can result in is at very special values of theta, we end up getting a different left tangent and right tangent on the manifold. This sort of non-differentiability is not addressable through this multi-scale regularization. These cusps will persist at every scale, despite how we may try to regularize the manifold. But, arguably the good news is these are things that these are problems that are uncovered by taking this manifold geometric approach, and they give us a warning of what we may need to look out for. And this can actually be dealt with if we're doing a parameter estimation problem. We just need to think about, are we actually on the left side of this cusp, or are we on the right side, and then use the appropriate tangent vectors. So here's one quick example to show how this can arise. Here's a model of a 3D slab, and we're going to watch what happens to this slab as we change the pitch. We're going to watch it as the pitch goes back. Ultimately, we'll consider a 3D model for this where we can also change the roll and the yaw of this object. Okay, so let's watch this as it starts to pitch back. And what we see is that there's two edges at the top of this slab. And as we approach, or as we suddenly reach this very special parameter value, when we're viewing the slab perfectly head-on, we now have just one edge at the top of the slab. And then a new edge will appear at the bottom of the slab. So these changes, because of this construction of the object and the fact that we were viewing it perfectly head-on, happen instantaneously. We go from having two edges to one edge, or vice versa, instantaneously in terms of theta. And that causes these differing tangents. So we can see this experimentally. Let's take this to the extreme where we're viewing the slab perfectly head-on, both sort of vertically and horizontally here. If we look for the approximate tangent vectors at some scale as we change the roll parameter, so we're just sort of rotating this square in the plane and no new edges are appearing or disappearing, then if we roll left or roll right, we actually get the same estimate for the tangent parameter, for the tangent vector. So the tangent space as a function of the roll parameter really is one-dimensional. There's one meaningful tangent. In terms of the pitch, though, if we pitch forward or pitch back, we actually get different tangent vectors. These look sort of similar in nature, but they are formally different. They point in different directions. And so there are two important tangents at that point in describing the pitch. And similarly for the yaw, there are two tangents. So this 3D manifold, a three-dimensional manifold which should have a three-dimensional tangent space, at least once it's smoothed out, actually has a five-dimensional tangent space at this very special point. And that's something that can and probably should be dealt with explicitly when we're solving these parameter estimation problems. Don't have examples working this into the parameter estimation techniques, but this is again just a lesson that can be learned by taking this geometric perspective on the manifold problem. The final thing I'd like to talk about, and how am I doing on time? Doing okay? The final thing I'd like to talk about is compressive sensing and how we can take this geometric thinking about manifolds and somewhat the differentiability aspects of manifolds and plug them in as a model to be used for recovery of signals in compressive sensing. Okay, first, what is compressive sensing? One of the ways of motivating compressive sensing is the following, and maybe I could say this in terms of an imaging system. So conventionally, with conventional sensors or imagers, we want a lot of data. We want high-resolution images, and so we collect an n pixel image where n tends to be as large as we can really make it. So easily on the order of millions. But we know that the information in X is compressible. So at least what consumer cameras do is almost always to immediately compress the million or 10 million numbers that they record down to some smaller set of numbers. And they do this because there's structure in real-world images which can be exploited, very much in the spirit of everything else I've talked about today. But in a sense, it kind of means we're not really getting the most bang for the buck out of our sensing or our imaging architecture, right? Because all of these numbers we've recorded, all of this, the sensors we built into the system are recording information that is redundant and it allows us to throw some of it away without really suffering too much in terms of quality of our image. So compressive sensing proposes a new way of acquiring these high-dimensional signals. Instead of taking in measurements, which can be huge for X, we record only M measurements. We represent those as a vector Y, and the relationship between Y and the image we actually want is a linear relationship. We can represent it as a matrix multiplication, Y equals phi X, where typically phi is a matrix populated with random entries. And so what this means, if you just figure out that this measurement in Y is the product of that row of phi with X, what this means is that every measurement in Y is just a random sum of the pixel values in our image X. And each measurement we take is just a different random sum of those pixel values. And compressive sensing is not only proposed for imaging, but for other types of signal processing. For example, processing RF signals or three-dimensional video signals or hyperspectral images, all kinds of signals where it's expensive or difficult either to physically measure the signal or to subsequently compress the signal. Then these are good motivating applications where we might want to think about taking a small number of random measurements. Okay, so for those who are familiar with linear algebra, when we see an equation like this, y equals phi x, and I ask you, I say, given y, can you tell me what x was? If you see a picture like this, the answer is usually no, because this is an underdetermined set of linear equations. There are more unknowns than there are constraints available. And so there are, in fact, an infinite number of candidate images which could generate the measurements that we measure. But in compressive sensing, we can resolve that ambiguity surprisingly accurately by having a good model for how X behaves. The typical model in compressive sensing is that we assume X is actually k-sparse in some basis. So for example, in the wavelet basis, we might assume that X has only k non-zero coefficients at some positions that we don't need to know. Or in the Fourier basis, maybe it has k non-zero coefficients at some frequencies that we don't know. If we can make this assumption of sparsity, and if we take a number of measurements that's just proportional to k log n, and usually in practice like 3k or 4k works very well for compressive sensing, then we can resolve that ambiguity. We can say even though there's an infinite number of signals X that agree with the measurements Y, actually, very frequently, it's the case that only one of those candidates is sparse. Out of an infinite set of possible candidates, only one of them is sparse, and there are good algorithmic ways of finding that sparse solution. So this is how compressive sensing works. You take random measurements of a signal, and then you recover that signal using this model of sparsity. Compressive sensing has inspired a number of practical and ongoing prototypes for actual sensing architectures that can take random measurements of signals. Just to give an example of an imaging system that was proposed while I was a grad student at Rice, this is a single pixel camera that was prototyped there. So the idea in this single pixel architecture is that we have an image focused onto some plane, and at that plane we replace the conventional detector, conventional CCD detector, with an array of digital micromirrors. Each one of those mirrors can be independently flipped into one of two states. Those that are in the on state reflect the light up through a second lens, and that focuses the light onto a single photodetector. So what that photodetector is measuring, the light intensity at that photodetector, is the sum of the pixel values of the image at a randomly selected set of half of the pixels. And then we can change the pattern on the mirror array, record another number at the single photodetector, change the pattern again and record another number, and so on. Now, this may sound like a little bit of a burden, and indeed it's not meant to replace every single type of imaging that we might be interested in doing. I mean, cameras are so cheap that they, now are in our cell phones with 5 or more megapixels. But this type of sensing architecture might be useful for doing things like video sensing, where good video compression is algorithmically difficult to do. This could be good for sensing also at non-visible wavelengths. So conventional CCD detectors do not work well, say, for certain infrared ranges. And good infrared imaging systems can be very expensive, in the many thousands or hundreds of thousands of dollars. But this would be a way of imaging an infrared scene where we only need to plug in one infrared light detector instead of an array of light detectors. And similarly, people have proposed using these architectures for things like hyperspectral imaging. Just sticking in the visible wavelengths, these are a couple of the early experiments of actual images that were acquired using the Rice prototype, where the number of measurements collected was only 40% of the total number of pixels in the image. Since then, the team has been looking at some of these more exotic applications, things like infrared imaging. To plug manifolds into this, let me illustrate geometrically why compressive sensing works. So compressive sensing uses this model assumption of sparsity in order to permit recovering a signal from its random measurements. As I mentioned earlier, a sparse signal can be viewed as living along one of this union of planes in this high-dimensional space Rn. What's known in compressive sensing is that if you take about k log n measurements, so k log n is sort of the magic number of measurements you need for all these nice properties to kick in. If you take k log n random measurements, so m is the number of measurements, then with high probability you're going to get a very nice stable embedding of that signal family in this measurement space Rm. Meaning no two images are going to land on the same point, and even more than that, you're going to preserve distances between any pair of sparse signals. So that distance preservation really shows you that the information required to discriminate those sparse signals is preserved when you've got these random measurements. Now there's more to say about algorithmically why you can recover those efficiently, but that's beyond this talk for right now. What we've been able to show is that very similar statements hold for manifolds. If we have a k-dimensional manifold in our high-dimensional space, and we take about k log n random measurements, where k now is the manifold dimension, not the sparsity level, then we'll get a stable embedding of that manifold in this space, where again, pairwise distances are preserved and no two signals get mapped onto the same point. So that shows you, if you could imagine if you had some measurement vector that lived here, you could try to solve this parameter estimation problem by projecting it onto the manifold and finding the best fit point. There's a catch though. Well, let me say, the good news is that when this is appropriate, when we have a good manifold model, the dimension of the manifold k can be much, much lower, even on the order of 2 or 3 or 10, can be much lower than the sparsity level of those same signals in any basis, like the wavelet basis. Sparsity of images is usually on the order of thousands, not on the order of 1 or 10. So we can do these manifold-based signal recoveries using many fewer measurements when it's appropriate. The one catch is the theory we have for embedding these manifolds pertains only to smooth manifolds, not to the non-differentiable manifolds that I've been interested in this talk. But we can address that problem by using this regularization technique. We can do it by building the regularization into the measurement process. So as we measure these sharp images, we're going to do so we're going to correlate those images with functions that look random, like Gaussian noise, say, but also that have been filtered at a sequence of scales. And that filtering gives us this, this multi-scale structure, makes it accessible so that we can use it in solving the parameter estimation problem. So here's just one example of solving this parameter estimation problem from compressive measurements. We go back to the problem of finding the parameters of an ellipse. Here's our initial guess for the parameter that we feed to the algorithm, and this is how far off we are when we begin. We deal with images that have 16,000 pixels, and again we're on a manifold that has dimension 5 that is not differentiable. We want to estimate the parameters of the ellipse given random projections of this original image. If we take 6 random measurements at each of 5 scales for a total of 30 measurements and randomize over that measurement matrix, then in 57% of the trials, when we start from this initial guess, we converge to the true parameters of the ellipse. To drive that success rate up to 99% of the trials over a random sensing matrix, we need about 100 total measurements. But this number of 100 measurements for image processing and compressive sensing is very small. If we were going to try to recover this image using sparsity-based compressive sensing, we would need many more than 100 measurements because the sparsity level of that image in this image is probably at least on the order of 1,000. The last example I'll show is that we can also use these manifold models for recovery of multi-signal ensembles. If we have not just one image we want to acquire, but a whole sampling of images, so maybe I have cameras positioned all over some field and I want to take a bunch of pictures and then reconstruct them all, I can use that manifold structure to reconstruct the ensemble of images. Here's a synthetic example where I imagine we have a collection of satellites viewing some scene from different positions that are actually unknown to the algorithm. And we ask each one just to give us 96 random measurements, a total of 96 measurements each from 5 different spatial scales. If we try to do image by image reconstruction just using sparsity, we do a very poor job of reconstructing the ensemble because 96 measurements per image is very, very few. But if we use this manifold structure, we can actually discover the positions of all the cameras and reconstruct the ensemble of images very accurately and get a much more clear reconstruction of the underlying scene. So finally, to conclude, I've talked a lot about the insights we can gain into signal and image processing by taking a geometric perspective on where our signals live. I focused a lot on manifolds and 2 types of non-differentiability that both arise due to the movement of sharp edges. One of them can be addressed through this multi-scale regularization procedure. The other one, which is only local, cannot be addressed with that regularization procedure. And then I've also talked about how this insight into the geometric structure of concise models can lead us to other applications, things like compressive sensing, where we can replace the conventional sparsity-based models with manifold models. So with that, I thank you very much for coming. Thank you for your time.
So we have time for a couple of questions.
I'm sort of interested if you could comment more on taking initial guesses for your enumeration, because it seems like as you look at smaller scales, more and more local minima that you'll have.
Right, so this is why you want to start at a coarse scale. The coarser that your scale is where you start, the more forgiving it is in terms of picking your initial guess. I guess I can't give you any very systematic answer in terms of how accurate that initial guess needs to be. In principle, that should be answerable from this type of geometric viewpoint, but it would require some computations that we still haven't quite done.
So you mentioned when you were doing work with the occlusion-based non-differentiability that you could get around that problem by using either the left or the right.
Right.
How would you actually detect, or how how would it make itself apparent that you were at that cost?
Yeah, I think it would, if you're designing the algorithm, you already have a model for generating the images themselves. You know what you're looking for, you just don't know theta yet. So if you have that level of knowledge about the model, then you can try to identify sort of, with a little bit of human intervention perhaps, where these special articulation points are in which edges can suddenly appear or disappear. Probably they're also discoverable numerically, maybe by trying things like these regularization approaches and looking for points for which the dimension doesn't actually drop, despite the fact that you've regularized out the manifold.
That's one more question.
So in this case, you have some model for the manifold.
Right.
Would you consider that some of the capacitive sensing ideas could be applied to cases where there exists some underlying manifold,
Mm-hmm.
but you cannot exhibit some parameterization or you don't have a clean way to characterize?
Yeah, you certainly don't need a closed form way of characterizing the manifold. In fact, if you just have a sampling of points, then you should be able to adapt pretty much all of the ideas that I've talked about here using that sampling. You could still construct a kind of a multi-scale tangent exploration of that discrete data set and then use that to navigate that data set to try to converge to your best estimate.
Okay. I'm sure that he will be available to answer more questions later, or you can go to visit him.
Yeah, not far.
Thanks, Professor Wakin.
Thank you very much.